So welcome everyone to the data management session. So I'm Vincent Ardion from Mac4 Laboratory. I'm co-chairing with Paul. Paul?
Yes, I'm here. Good morning, good afternoon, and good evening. Welcome to the data management session.
So I just want to take a few minutes to record the guideline for the session. So please, for all the speakers, stay on time. We have a tight schedule, so it's 12 minutes. And hopefully there will be time for question. So you can use your VOVA application on the Q&A or raise your hand in Zoom. But I think it's better in VOVA. I will invite the first speaker to be ready. Heinz, are you?
Yeah, I'm ready.
Yeah, okay. Welcome Heinz Junkes from Fritz Haber Institute. He's head of the IT group. Heinz will present FARMAT, a proposed consortium of the German research data infrastructure. So the stage is for you.
Okay, thank you for the nice introduction. You have to switch to the full mode, I think, because I will not share. I will. Yeah. Okay, so I can't see myself. Okay, okay, that's yeah. Well, okay, now that's the right one. Okay.
We don't see your. We see only your slide in your.
Yeah, I will not share. I will present it like this, like a Betterman show or whatever. That's the idea behind this. Okay, on behalf of my colleagues from the FARMAT, I will just present this consortium, which gets funded by the German research data infrastructure. It's called in German Nationale Forschungsdateninfrastruktur. And the idea behind the German initiative for the research data infrastructure is the systematic management of scientific and research data. And above all, there's about storage and availability are also addressed. And you know, everyone is now talking about fair data handling. And this fair is for findable, accessible, interchangeable, and researchable. No, this was the wrong, interoperable and reusable. That was the synonym for this. And within this Forschung data infrastructure, we get funding for a project called FARMAT. And this is a project which deals with infrastructure for condensed matter physics and chemical physics of solids. And the idea is by building a fair research data infrastructure for these fields, the consortium will lift the treasure trove of materials data and therewith contribute to a disruptive change in the way science and R&D are conducted. This is from the proposal line, and therefore it gets funded. And special within the FARMAT, the acronym, this AI is also interpreted as artificial intelligence, and we are just one part of the FARMAT consortium, and we are dealing with the data acquisition. I will show the different areas in this FARMAT consortium, and we are just part of the artificial for the data acquisition. And you will see there are different areas, and the area A is synthesis. And in this context, this is dedicated to the full characterization of samples and the corresponding synthesis and growth processes. And these information are really crucial for the reproducibility of materials and their properties with given quality. And the specific task will consider various synthesis routes, like from gas, liquid, and solid phases, and by assembly. And then there is the area B. Okay, I have to go in the wrong direction. It's new for me. This is the area B. And the area B covers the microscopic characterization of materials by a broad variety of measurement techniques. And each of them comes with specific challenges concerning processing, preparation, and storage, owing to differences in volume, velocity, and data formats. And in the first phase, we try to approach, or we go for a selection of experimental probes in the area of physics and chemists, and they will deal with electron microscopy and pulse probe experiments and like this. And then there is the area C, it's theory and computational, and in this field they have a lot of experience already in this consortium, because there is another funded project called NOMAD, and they deal with numerical techniques to compute material properties. And in these, they are well known in this field. And then there is the area D, the digital infrastructure. And within this digital infrastructure, this is a praise to all other areas, it's sure. But in this area, we will the specific task will be dedicated to processing and decentralized storage, creating a network of data hubs at different locations. And the Fermat portal, this should be a web-based graphical user interface, will also include materials encyclopedia. And in this part, we will also deal with electronic lab notebooks and laboratory information management systems. And also there will be a tight collaboration with HPC centers. And in this area, we will implement a special data acquisition system. And there's another area that is the area for the use case demonstrators. In this area, we will deal with in the fields of the battery materials, spintronics, magnetism, metal-organic frameworks, biological physics, and also with artificial intelligence. And then there is another very, very, very important area, F. This is for the user support, training, and outreach. And we will reflect our concept for how to engage with the community to allow researchers to make use and handle the Fermat tools. A variety of workshops and other training opportunities will be offered, and support from connecting data hubs to the overall data infrastructure. It should not be an infrastructure just in Germany, but we get the funding from the German government, and therefore it's part of the national or the national Forschungsdata infrastructure, but we will also connect it to the whole community. And unavoidable, there will be an area G, administration and coordination. I assume that most of the people hired for this consortium will end up in this area, but nevertheless, we will do our work on the very, very low end here on the configurable experimental control system. And therefore, we will try to implement, that means this is our part here, on this area is our part at a very, very low end. But we will try to create an easy to configure software environment for data, for measurement and data acquisition and documentation in this area task D. And the problem we are faced with is that, especially for smaller experiments or smaller institutions, there is no support for systems like EPICS or Tango. they can't use it because they have no people working on this. It's in this environment here in the ICALEPCS, you all talk about perfect control system. You're all using perfect control system, but in small institutions, there is no perfect control system. And we will try, here we have to make a low threshold offer to be able to use such systems. And even such systems are also mostly not used in teaching at universities. No one knows how to deal with these systems. And that's why we started right there with our task D5 in the university. And our partner is from the Friedrich Alexander University in Erlangen. And they already developed a prototype software for experimental control with uniform and documented data outputs, and this has been used for years. And this is done at the university, but unfortunately, or as usual in universities, they do not have access to this perfect control systems, and therefore they have done it with LabVIEW. And for the user, it's perfect, and it's proven by itself by using in research and teaching, but it does not satisfy the FAIR rules because they are using a LabVIEW or they're using proprietary systems, which are closed systems. That means by using this LabVIEW, for example, it's not bad and they're happy with this, but it's not open source. It's not operating system independent. It's not platform independent. It's very poorly scalable. And therefore we want
two minutes left.
Therefore, we want to implement an advanced the EPIC system as a base system for recording, automatic metadata tagging and storing, archiving and managing research data. This is the sentence from our proposal, and therefore we got the money. And what we try to do is we want to use the interface they have developed in their system with the LabVIEW. Might be we will change it to Python or graphic stuff or whatever. But the idea is to generate for this low threshold system where the user can only click on the systems, then we will create a JSON string or whatever that can be used as an input for the recipes for Blue Sky. Every one of you know that this is Blue Sky because this is the typical Blue Sky framework and the task which runs on Blue Sky. And we will try to implement this configure. We have already implemented this easy to configure system. This will create a template which can be used as Blue Sky, and then the experiment can run on it. And with this step, we allow the users that they can use the configuration tool to create a template which then they can change and to adapt it more to experiment it if they are interested in. And the same stuff we want to implement is our next step, that out of the Python Blue Sky stuff, we will generate database files for the EPICS environment. That means we can move some parts to the EPICS part, but even with readable JSON script or whatever. And this will enable also the chemists, which are not IT affine like physics, they deal with such called handbooks. For example, in the catalyst research, they have handbooks which defines what have to be done with the probes and with the samples. And out of this handbooks, we will also generate a template for the Blue Sky stuff, and will use the Blue Sky, this part as a recipe for the Blue Skies to get the fair data handling and to use the Blue Sky environment for storing data, to finding data, and all these stuff. This is the idea behind. And I thanks to Abdurrahman Moshantaf, who has done most of the part already in the new created ICALEPCS system, and even thanks to Johannes Lehmeyer and Alexander Pfau from the Friedrich Alexander University. And this is my last slide. I got asked from Mike Fedorov on the session where we tested the equipment, and he asked me how we have done the setup with our film studio. And therefore, thanks to Sven, and these are the images for our film studio with the green wall I'm in front of and the mixing system to put on these films. Nowadays, this is very often asked for, and therefore we have implemented such a film studio. Thank you for your attention. Hope you enjoyed it, and thank you.
Thank you for this fantastic presentation. There is a time for a short question. Bova, or yeah, so there is a question from Timo. Let's see. Timo? Not sure. The question is, have you defined the data format that will be used, for example, HDF5?
Yeah, we will use HDF5, but it's other parts of the consortium task B. They should define a file system structure and metadata and ornithology for these data. And if they are ready with this task, then we will adapt our format to their special format, but actually write everything readable in HDF5 files and store them and deal with them. Yeah. And we will see what happens with the other tasks. We have already started to do our task, and then we will wait for the input from the others.
Thank you, Hans. We have to move on the second presentation.
Okay, let me introduce the second talk, which will be delivered by Dr. Huihui Liu from SSRF, the host institute. She's going to talk about the prototype of image acquisition and the storage system for Shine. Huihui, please take away. Start your.
Hi, Paul. Can you hear me? Hello, everyone.
Yeah, we see your presenter.
Can you see my screen?
Yeah, can you try to change?
Can you see my screen? Yeah. Okay. Hello, everyone. It's my pleasure to have this opportunity to share my work. My name is Huihui. I come from Shanghai Advanced Research Institute, Chinese Academy of Sciences. And the subject of my presentation is prototype or image acquisition and storage system for Shine. And the presentation includes 4 parts. First of all, the motivation. Then I will explain the details about the architecture, such as the image acquisition, transmission, storage, retrieval, and online display. We also did some tests to check the performance of the entire system. That's the summary. Shine is a quasi-continuous wave-guide X-ray-free electron laser facility. It's under construction now. While a myriad of image data will be generated by the beam monitor system, the optical diagnostic system, and the laser system, so we need an efficient data acquisition and storage framework to accommodate such high-speed streams of image data. It's about 1,000 megabytes per second. Before we did this work, we researched available commercial cameras and its corresponding storage mechanism. As you can see from this figure, the commercial products usually acquire the images for less than 1 minute, and then archive images in a local buffer. After the images, then the images will be offloaded to the offline storage through network or image USB. After that, the camera can take the next acquisition. Since it cannot continuously perform acquisition and storage operations, it does not meet our continuous operation requirements. We also researched what other facilities did to handle high frame images. However, most of them are built for beam lines. Usually, it's a dedicated system with readouts, big or even high-speed network. We want to build a general image system which is less expensive and using regular commercial hardware. Therefore, we developed the system with camera-link cameras, DMQ protocol for data transferring, HDF5 and MongoDB for data storage. Details as follows. The figure shown here is the system architecture. It can be divided into 5 functional modules as colors in the diagram. 2 CCD cameras with camera-link interfaces take pictures at the same time. One camera is directly connected to a frame grabber through a cable. The other is connected to a frame extender through a fiber cable. That solves a distance limitation. Images are processed and packaged by the acquisition server and then transmitted to the storage server and the online display server. The data transmission is through 10 gigabit Ethernet using DMQ protocol for the data transferring. After storage server receives the data, it first appends it and then saves the image data in files and database. The web-based retrieval system is based on standard Java 2 platform enterprise edition. It's designed to handle the remote queries for the saved records. The online display server can display the images captured from the 2 cameras in real time, as well as the metadata related to the image. The photos shown here are the hardware and the test. First, the acquisition module. There are 3 commonly used camera interfaces as shown in this table. Taking cost and performance into consideration, we choose camera link and utilize a range extender to solve the distance limitation. There are 2 cameras on the system. One is directly connected to the camera link frame grabber. It's about 10 meters. The other is connected to a range extender or a fiber cable. The system is constructed of 2 converters. One is on the camera link side and one on the camera link frame grabber side. Camera link frame grabber is a PCI Express-based device. It allows high bandwidth communication between the device and the motherboard. Next part is the image transmission. We make use of DMQ for image communication. More specifically, as shown in this figure, we use request, reply, and publish subscribe patterns through TCP channels. Request reply pattern implements the handshaking before the transfer of data. One server must shake hands with the other to ensure the translation synchronously. However, the request reply pattern depends on the fixed send to receive and receive to send sequence. The connection will be interrupted if the sender does not receive any reply. In order to solve this problem, we modify the configuration, several configuration parameters to realize that even if the sender does not receive any reply, it can continue to ask until the handshake is successful. The publish subscribe pattern connects the acquisition server and the online display server, the storage server. It's used for one-to-many distribution of data from a single publisher to multiple subscribers. The acquisition server publishes a stream of image data, and the 2 clients consume that stream. However, in order to increase the transmitting speed, we bind 2 network interfaces into a single logical bounded interface. A network bounding increases a network throughput and bandwidth, but network bounding increases the CPU consumption and reduces the overall performance. So we use 2 networks logically, and in our program, the data are transmitted through 2 networks. However, we encountered another problem now. When two network ports transmit data simultaneously, some packages are lost and some packages are duplicates. This is due to the disorderly contention between the threads. So we optimize the execution of the threads and add several mutex locks. Then the transmitting speed increases to 1,200 megabytes per second. Next part, the storage. The image data represents an image, and the metadata includes details about the image. We have designed 4 schemas for storage to see which one has the best performance. Schema 1, both the image data and the metadata are stored in MongoDB. Schema 2, we make use of HDF file to store the image data and use MongoDB to store the metadata, and the metadata is the index to store the image data. Schema 3, MongoDB is replaced by Cassandra. Schema 4, similar to schema 2, we use the HDF file direct trunk write strategy to write the data to HDF file. The storage performance is tested on this server using 3 different sizes of 3-level image. The storage speed is compared between 4 schemas. As we can see from these pictures, to use MongoDB to store the metadata and HDF files direct trunk write to store the image data can provide the optimal storage performance. It's about 1,200 megabytes per second. We have also monitored the CPU and memory utilization before, during, and after the storage program running. Here is the test results. Anyway, the CPU utilization is not the bottleneck limiting the throughout. The memory load is not the bottleneck either. So we can infer that the storage performance is greatly influenced by the hard disk. So far, we have found optimal storage schema. It seems to be difficult to increase the speed from the software design. So as to achieve a higher storage speed, we can consider to extend the hardware. So we use 3 servers to deploy a raster file system and configure 2 clients mounting to the system. We use 10 gigabit Ethernet. The storage performance is tested in the cluster. It's about 1,500. It shows that the cluster can provide a better performance. This paper published in A. It introduces details about the image storage. The next part, image retrieval. The retrieval system is based on Maven Java 2 Enterprise Edition class-based platform. The architecture is composed by 3 parts. The persistent layer, the business logic layer, and the client layer. Data API uses database connector to connect to the MongoDB database to get a specific images index. With the index to the HDL files, it uses a Java HDL file interface to access the image HDL file format. This is the web display interface. One can select a camera and take a period of time to search images. Pop up a more detailed time for selection. This is a retrieved image. The last part, online display. We use PyDM to build graphic user interface. As shown in this figure, the image data are transmitted through DMQ crystal from the acquisition server and then imported to an EPEX database by Sky interface. The total number of image frames acquired from the acquisition server is also displayed on the interface, compared with the number of images having been stored into the storage server. The 2 are equal, and it can indicate that there's no package lost. Test is taken by 2 cameras. The cameras are illuminated by a diode. The diode is excited by a sine wave signal generator. We acquired and stored image data for a period of time, according to all the images from one camera within 2 seconds. We find the brightest point of each image. That is the point with the largest free value. Then we fit a sine curve using the least squares method. The fitting frequency is equal to the frequency of the signal.
1 minute
generator.
left.
Okay, sorry. We also test the performance for higher speed, 1000 frames per second. This time, we monitor the number of HDR files generated every 5 seconds by the Linux command. This is a test result. The number of files is more than 10 for a period of time. We can calculate the storage speed, 1000 megabytes per second. So far, the system is able to acquire, transmit, and store image data at a speed of 1000 megabytes per second. The solution is based on camera-link interface, GMQ protocol for transferring MongoDB and HDR for data storage. The utilization of multi-thread programming and multi-network ports also increases the system's performance. The hardware architecture data. It could also handle the waveform data for SHAN. Thank you.
Thank you for the nice talk and the work. We have one question now. How do you trigger the cameras? And how do you attach a pulse ID and the timestamp to the acquired frames?
Yeah, we use alt trigger. And you can see from step. Use the time step.
Okay. Any other questions? We still have a couple minutes time.
I have a question, if you don't mind.
Yeah, go ahead.
Yeah. So the online display, does the online display receive all the image, like the storage?
Online display.
Yeah. Here on the
retrieved image is the
I think we have a problem of sound now.
We have another question on the Hoover. How do you organize the data in HDF5 or Nexus? So it's pretty much HDF5.
Any metadata in HDF5. The metadata is managed by MongoDB database because we think database is convenient for searchability.
Okay. I guess the time is up. Thank you very much for your talk, and we'll move on to the next one. If there's any questions, we can just ask on the Hoover.
So the next speaker is Jonas Nilsson from the European Spallation Source. Is a software scientist there, and Jonas will talk about managing high performance data flow and file structure. Please, Jonas, the stage is for you.
Thank you. So let's get started. I've, for the past few years, worked with data processing pipeline at ESS, So I'll be talking to you about that specifically, as made obvious by the title, I hope. I'll give you increasing ridiculous similitudes before I'll get to the actual meat of how things are working. But let's start with the ridiculous similitudes. So we have a problem. We will have, well, initially only 3 beam lines when we come online with a beam on target at ESS, but in relatively short order we expect to have 15 beam lines, which means that we'll have data from very disparate sources in terms of types of data and data rate and such things. And we don't expect us to have the manpower to be able to handle this, handle all these beam lines with unique file writing systems or data management data pipelines, basically. So we want a system that can handle very disparate data sources to reduce the workload on us, basically. We also require this system to have a high throughput. And now I know that the throughput at the data throughput at a neutron facility is in many ways often relatively small in comparison to synchrotron sources. But all in the grand scheme of things, in comparison to neutron sources, we will still be able to, we will still have to support 15+ beam lines at some point in time. Now, this could of course be done either through one system with a huge throughput or many smaller systems which in conjunction with each other would be able to have a similar throughput. Furthermore, because we want to have a single system in use for all the beam lines, it's also a requirement that it's be easily configurable, because we will be bringing on a lot of beam lines in relatively short order, and we expect changes to those beam lines as time goes on, because that's just how things work at research facilities. So the solutions that we've decided on is that we want to use a data aggregator, because that gives us some flexibility in handling the data and basically running many simultaneous writing jobs, because the data aggregator gives us a bit of a buffer in terms of how quickly we need to handle the data. We don't necessarily have to do it in the instant that the data is made available. Also, we do not want to have one or a few file writers available for each and every beamline, but rather we want to have a huge pool of file writers that are available to all the beamlines. This gives us some flexibility in terms of, well, if we see that the facility is under heavy load and that we're quickly running out of idle file writers, then we can add file writers as required. But it also means that if we find an issue, in principle, we can then replace available file writers with an updated version as they go idle, and in at least theory do live updates of the software that we're using. Now, as a consequence of this, we of course require that the file writers that we are using are dynamically configurable for the task that it is given, i.e. if a file writer is given a task to write data from a specific beamline, it should be configured for that beamline. And of course, because of the time frames we're talking about, we require a graphical user interface application for designing the file layouts and the origins of well, where the specific data source from a specific beamline will be placed in a file that is to be created for that beamline. Right, so let's look at a pipeline, data pipeline in detail. So at first we will have this graphical user interface application for designing the file layout as mentioned. That provides us with in practice a JSON file that describes the file layout. Those JSON files, those template layout files, will be made available to or used by the experiment control application for each and individual beamline. So each and every beamline will have its own instance of the experiment control application. And that application will then use that template to create a new file writing job when the user requires or commands the experiment control application to create a new file writing job. When a new file writing job is created, it's posted to a file writing job channel in the data aggregator, from where it is picked up by a single file writer in the file writer pool. In practice, well, we can consider it random which file writer picks up a file writing job. It's not actually random, but it might as well be. So when a random file writer has picked up a file writing job, that file writer disconnects from the file writer pool basically, and instead connects to the channels in the data aggregator that holds the has the data that we're interested in for this particular file writing job. It also connects to a command and control channel that is made available through the data aggregator, which the experiment control application for that particular beamline can use for directly controlling the file writer that we are currently using. In practice, this means stopping the file writer when the user considers the current experiment run to be done. But it could also be things like making minor modifications to how the writing is done, though that is somewhat limited in scope what you can do through that. It's mostly for stopping the file writing job. When the file writer is done, the file has been closed and everything is good and done. The file writer is connects to the pool again. It connects to the channel where it listens for new jobs and thus becomes a part of the file writing pool again. Now, because of this system, you can actually have many simultaneous file writers listening in and consuming data from the channels, the same channel for a specific beamline. So that's one of the upsides of using a data aggregator and this kind of layout as well. Just a quick look at the user interfaces. For those of you familiar, we're using Nikos for experiment control. Nikos provides us with a Python interface for running an experiment. It also gives us a graphical user interface view of some of the devices, at least the devices important for the user that are available. In this particular case, in this slightly simple, somewhat simple example, the experiment control application shows us the status of the currently used file writer, as in its current writing. Yeah. This is an example of the application that we're using for creating the file layout. It has a graphical view of the location of the devices on the beamline. In this case, a couple of choppers, the sample, and some other device. And it gives us a tree view of those devices and the ability to make changes to the position and data sources and, everything we need, basically. The actual output of this application is, as I said, JSON code. Don't have to look too closely at this, but you have directories and you have metadata, and you can configure data streams. And static data sets, i.e. data sets that only are written to when the file writing job is created, but is otherwise static. There is also support for links and a few other structures as well. Right, so if all this seems to be of any interest to any one of you, please feel free to get in contact. The Nexus constructor, the GUI application for creating the file layouts is open source. It can be found on our GitHub page. In my opinion, it's not quite yet ready for general consumption, but we're getting there. As mentioned, we're using Nikos for experiment control. We create a Python, simple Python library for creating and posting jobs. We use Apache Kafka for data aggregation. We have an open source file writer that is now close to being feature complete, in my opinion. And of course, obviously, if you didn't figure it out by now, we use HDF5 for data storage and the Nexus standard on top of that for the layout, or well, the Nexus standard for how to store data in the HDF5 file. So that is basically it.
Thank you, Jonas, to be right on time. So we have a question from Mitchell. So Mitchell, you're allowed to talk. Mitchell. Okay, so we have Shu that has a question as well.
Sorry, that should be a mistake.
Ah, okay.
Sorry.
Sorry. So we have a question on the QA. Does all the data is streamed into your Kafka server? Thanks. It's a question from Wong Ziu.
The very short answer to that is yes. All the data is streamed into our cluster of Kafka brokers, as they're called.
Okay, let's come back to Mitchell. If you want to talk, it's now. So thank you, Jonas. I think it's time to move on to the next presenter.
Okay, the next talk will be given by Dr. Tong Zhang from FRIP, Michigan State University. He will talk about manage the physics settings on the modern accelerator. Dr. Zhang, please take away.
Thanks. Can you hear me?
Yes.
Yeah. So can you see my screen? This is for presentation mode.
Yes.
Yeah.
Just flip the pages if we
okay.
can see that.
Thanks.
Okay, it's good.
For the introduction. I'm from AFRIP at Michigan State University. I'm a controls scientist working for the high-level applications. Now, today, I'd like to present the way that how we manage the data at this modern accelerator. And I will give a brief introduction for this project, and then overview some the data perspective for this controls network. So the AFRIP project is a new project that taken years ago that it is aiming to accelerate the full range of realized ion from the helium to oxygen to uranium with some power at the deposit at the target at 400 kilowatts to produce rare isotope that cannot be found on the Earth, to boost the nuclear scientist research in the United States and the world. So now in the past maybe 4 years, we started the commissioning, and at 2017, and we started from this ion source, and then the front end, and then we moved to the Linux segment 1, folding segment 1, and Linux segment 2, and folding segment 2, and then reached to the now we are here at the beam derivative system. The next phase is the generate the reisotope beams in the target system is scheduled the end of this year and early next year. So in order to achieve this, the quick commissioning, we developed this called fantasy framework for high-level physics controls. This is stands for the physics high-level applications and toolkit for accelerator system. This mainly does is that it can manage the device configurations, in a very portable and maintainable way as we move forward to the different segments of the accelerators. And from the code level, we abstract all this machine into Python with Python in object-oriented way. And you can do the online modeling with physics modeling code we developed. And it can features you can use it to interactively talk to the machine and compose very easy maintainable Python script. And we also developed this virtual accelerator system to develop applications. And then we have the client packages to integrate all these web services. So it is now running on our Debian Linux servers now in our control systems. And it's roughly deployed by more than 20 Debian packages and into the system together with our continuous integration and deployment system. Now this is the view of this project. Now it is you can treat this one as the first is core part, and another one is the UI part, because we heavily use the PyQt library to build our hardware applications. And this is the final software deployed to the control system. This is the PyQt applications. And mainly all these configuration files actually managed being separately. This is deployed by another package. As we move to different sections, this one is updated. And also we work with, Michigan State University has some other accelerators. We also are trying to migrate this one into their platform. And this is basically the workflow that we define these configurations for different segments. And then we use this core to instantiate everything into some unified interface, and then use this modularized UI component to build this general high-level applications. This is some detailed view about what happened inside. Basically, you want to talk to the machine. You do not want to talk to, this is kind of information distributed around this whole control system. It is not easy to find the useful information. Then what it does is that it aggregates all this information together to make it easy to reach the interesting information. And then you can just program into each the whole lattice. And then each lattice is composed of a sequence of elements, and each element has many fields you can control. So this is a kind of hierarchical tree view you can control in the terms of a device control perspective. And this is kind of the workflow that we first developed this application against the virtual accelerator, and then test everything you can do, and then deploy a test against the real accelerator and deploy. So this is one of the example that we manage the information. We call this is actually on our launcher system. We develop you develop lots of application, and you have lots of documents for this application, how you manage it, and how to help physicists to retrieve the useful information instantly. And then this is our solution that you put each card for each application you developed for beam tuning, and then each card can have a different description, how to use it, and you can expand it to see lots of different information. So that way we will not get lost when our development become huge and huge. So from the physics side, that we want to make use of all this data in the controls network. And then, the first layer is that we have all kinds of different devices, basically magnets and optics elements. And you have different information to describe this device information, like its location or device name, device control knobs. This is binded into some IOCs. And also we have, this one is handled in our framework. You can reach in some object-oriented way to access and control it. And how to talk to this web services to retrieve different kinds of valuable information. For example, you can ask alarm service to return alarm signal, and you can ask a channel finder to return the channel's information. And the most important thing is that you can ask archive appliance to return the historical archived data for analysis. And also you have another bigger information is OLOG services, which keeps all the memos when we tune the beam. And another part is we have physics data, that's how you handle the different physics quantity integration between different units. And all this information, we have the data client package to retrieve and control it. And another big part is we have the software IOCs, which is can be used to handle arbitrary computing. And this is kind of supporting our applications. And another big part is the physics models. We have the linear or nonlinear models, so how to manage the lattice file and how to manage the simulation result. How can you make this simulation result useful in terms of the machine tuning? So in this talk, I'd like to address some research that address these key points. For example, the first one is device information accessibility, and the physics tuning replicability and machine state data integrity. So as I just mentioned, that this fantasy framework actually can well manage all these physics info. For example, this is an example. After you build this proper machine configuration file, and then you can reach FRB Linux section by this way. And after that, this is I call the instantiate to this machine instance. And after that, you can, for example, you can search by this quad is just quadruple, and name. This is kind of regular expressions. You can put it. It will return a list of matched high-level elements. And then this is an example. For example, here, this is now a quadruple here. And then it has two categories of the properties. One is the static and another one dynamic. Static means that you cannot control. You can only query here. You can use the .syntax to check the name, check the length, check the position, check the type, and check the physics type, which is another alien to this family, but this is not a physicist aspect. And this is the index number. The most big important thing is that this is dynamic property. For example, here, this is a quadruple, and in the view of the physics controls, you can control either via I field or control via the physics field B2, which is in the unit of gradient. So either way can work properly to the device. Underneath is that we have the physics data, the unicorn physics data, unit interpretation to bind all this together. So the data source here is that you can grab all this, integrate all these different data sources together to make this operation. And another side is how to maintain that the tuning settings. Basically, we asked ourselves the question is how to maintain it easily, segment by segment, as we are progressing to the new segment, and how to correlate different kind of data source in one place, and how to make them easily to access and easy for the model interface. So this is kind of based on this layer, object-oriented reviewer, we can quickly build all this stuff in one application. So this is the one that we build, so-called settings manager. This is manage all these physics settings in one application here. It can pull the device info like this context menu. You can right-click and access. Thank you. And then we can fetch the machine state. Machine state is this is a snapshot to be taken. We can manage everything here. You can sort it. You can pull data, and you can also export the data as different data format: Excel sheet, CSV, HDF5, and you can search. And also it can integrate, talk to the Pi archive appliance. We developed this Pi, this client interface to archive appliance. So this is the kind of a view of this take the BPM readings together with the physics setting. And that way you can correlate the different data in one place. And also we use this way to pre-generate all the settings from model to expedite the machine tuning. And this is a tool we developed to retrieve the data from archive, because this is very important for future machine learning application. And this is the BPM distribution, and you can have this blank. This is the good tune, and based on this tune, we can ask a setting manager to return that what is the setting at this point. So all this information actually we integrate in our application for easy access and used in our commissioning. So the conclusion is that we developed this framework for both the script environment and the GUI application for the data management for machine tuning. Thank you.
Okay, thank you for the talk. We're now open for the questions. I see one in the Q&A. How does Fantasy differ from OFI, another Python device abstraction package used at other light sources in the US?
This is first of all, this is different. My understanding is OFIT is more general, that it can abstract everything regarding the device. But the Fantasy here, we are aiming to just abstract the information that's useful for the physics side, which means the most priority that we talk to the physics model and do everything we can do to support this kind of model-based tuning. Yeah, hope that answers this question. Yeah.
Okay, any other questions? I have one short one. What's the format for your configurations? Are they kept in a database?
Currently, most, I mean, 90% is not in the database, because it is designed that it can talk to the database. But you know, as this project is still progressing, we should make it as simple as possible to edit the data. So now currently the main medium is through the Excel sheet, manage everything in Excel sheet.
Okay, thanks. Is there any other questions? If not, and we'll thank the speaker and we move on to the next talk.
Thanks.
Yes, so the next talk, it's actually the last one of the session. Let me introduce Gerrit Günther. He's a scientist at the Helmholtz-Zentrum Berlin Institute. Gerrit will present the FAIR meets Emil, principle in practice. So the stage is for you.
Yes, thank you very much. I would like to present a project that we are currently working on within the Helmholtz metadata collaboration, which is newly founded. And here we try to apply the FAIR principles on a quite complex infrastructure. That's the one of EMIR, the Energy Material In Situ Laboratory in Berlin. And in my talk, I will first explain the infrastructure. of the instrument. Then I will address the FAIR principles in the sequence reusability, interoperability, accessibility, and findability, and how we want to improve them or the measures taken. And finally, I would like to put the things together and provide some workflows, so how the data is processed. EMIL is usually consists of a fully automated vacuum transfer system which connects various chambers where samples can be processed, so their properties are changed, and also could be analyzed with off-synchrotron analyzing systems, but we will here focus on the synchrotron end station CC1, which sits on the very end of this vacuum backbone and is connected to the BESI2 storage ring in Berlin. So so this instrument is in a commissioning phase, and from a data management point of view, we can think of it to consist of two parts. This on one hand, the EMIL part, which stores the location and the processes applied to a sample in a sample database. And we can also of a part that belongs to CC1, the end station, which consists of the blue sky control system, where the user operates the instrument. Some details about the blue sky control system will be given by William Smith in a separate talk on Friday. For our purposes, so the main feature here is that the blue sky control system stores all data in a Mongo database. So addressing the reusability, which is in principle the richness of metadata. So like most synchrotron experiments, CC will collect a lot of metadata automatically, which comes from sensors, motors, even detectors, the main data. But it will, such synchrotron instruments also often fails to save important data automatically on one hand, and the most important one is the sample information. And here we take several measures to get this information. On one hand, it's a very simple measure. We just introduce a pseudo sample access in the control software of Blue Sky, which is in principle a text field where the user can provide some additional information about the sample during the experiment. We implemented a readout routine to get the entire history of a sample from the EMIL sample database. And also we provide a graphical user interface where the user can manually enter the sample metadata or additional sample metadata. It is shown here in the bottom right. This graphical user interface is located at a separate server to have a minimum impact on the instrument. And in this graphical user interface, we also implement a readout routine to read out the proposal sample data that is, which has usually given by the user a few weeks ago when applying for the beam time. So also this information could be retrieved. So besides the sample information, there's another kind of information that is failed often to collect automatically, and these are the user's notes during the experiment. This is often written in a paper logbook, and here we provide an electronic option, an electronic logbook which is the same as used by the ESRF. And besides the user's input, we also provide a direct connection from the Blue Sky control system to send selected events to the electronic logbook. So another way to improve the reusability is the use of persistent identifiers to make important information unambiguous. So we implemented instrument PIDs for CC1 and other parts of EMIL to clearly state where the data comes from. Moreover, we make a connection to the higher level service ORCID to get ORCIDs for the users of the experimental team automatically. So concerning the interoperability, which is in principle the way the information is provided, we implement a conversion routine to convert the content of the Mongo database in a Nexus file format, which is standard. This is standard in X-ray and Newton science. And in principle, the Nexus definition language meets most of the interoperability criteria. Besides that, it has some other advantages. For example, it is supported by capable software. To make the data now accessible, we make connections from the electronic logbook, the proposal system, the HZB, and the Nexus files to the HZB repository, which is an instance of ICAT. This is also used, the software is used by other facilities. Here the information becomes accessible through a web interface using the HTTP protocol. It also supports an authentication system. So, but now we must increase the findability outside of the HZB, and for this we make a connection, or currently working on a connection to a higher level service, B2Find, which is a global search engine. As a prerequisite for this is the automatic assignment of PIDs to these raw data files. And this is currently work in progress, so that we can clearly identify these files ingested into the ICAT. And also the harmonization of metadata, of the metadata schema. We are currently working to optimize the findability of this data. Now I want to put the things together and present some workflows. In case of CC1, with a EMIL sample database, we think or suggest that assume that the data is quite complete, and so we can provide an automatic workflow where the Blue Sky control system starts the creation of the Nexus file automatically and ingested it to the ICAT. So in this case, there would be no additional workload for the user, and the data accuracy may be not optimum because the data is unseen by the scientist or the user before it is ingested to the repository. To account for this, we also apply this we call a single step process, where the user uses a graphical user interface to provide additional information, and then starts the Nexus file creation in the ICAT ingest repository. This needs some workload from the user, and may also the data accuracy may not be optimum because the final file is still unseen as a user.
2 minutes.
For this we provide a two-step process where the user starts the Nexus file creation. The content of the file is then displayed in the graphical user interface, and the user can change it and enrich it, add some more information, can rewrite the Nexus file, and when it meets its demands, then he ingested it to the ICAT repository. So that means there's a lot of workload for the user, but with the best data accuracy, we think. Drawback could be that the Nexus file creation may take a while depending on the file size. So yeah, to sum this up, we expect to meet the essential criteria of the FAIR maturity model soon. And maybe the main message here is that we increase the reusability mainly on the instrument level. And here it was an advantage that the instrument is still in its commissioning phase, because there was a quite dynamic process between the instrument control software and our data management group with mutually induced steps. So thank you very much.
Thank you, Gerrit, for the talk. There is time for a question. I have one, if you don't mind. This is about the FAIR maturity model. You have already an idea how you will assess the system with this model?
Yeah, and we have done this already. So yeah, a problem was that some of the criteria are quite unambiguous to us, or ambiguous to us. So it does not clearly state what richness of metadata, for example, means. So there might be some problem, but we do an assessment of this instrument. Yeah.
Yeah, I don't see any more questions. So thank you for your talk, and I think it's time for the close out of the data management session. So thank you all the speakers and also all the attendees, and I think it was a really good talk. So don't forget that after the session there is a poster session, and there is you can ask your question in the Q&A on the VOVA platform. So with that, thank you all, and see you soon. Bye.
Thank you for your attending. See you.